Hello and welcome. Just hit my hand on the table. So in this video, we're going to look at logarithmic differentiation. But before we do that, let's take a moment to review the log properties, or sometimes called the rules of logarithms. Log properties, we'll say. Let's start with log of a times b, where a and b just represent some kind of expressions. They could be, variables or numbers, doesn't really matter. So log of a times b. What does the log property say about the log of a times b? How can we rewrite that? If you said log of a plus log of b, and that's correct. That's the first log property, the one that deals with products inside logs. What about the log of a divided by b, or a over b? How does that expand? If you said log of a minus log of b, then that's correct. All right, and the last log property we'll look at is log of a to the power of b. How does that get rewritten using a log property? If you said b times log of a, then that's correct. That log property, the power comes down in front of the log. Now, you don't want to confuse that with the power rule of derivatives, which says if you're taking a derivative, the power gets multiplied in front, and then you subtract one from the exponent. That's when you're taking derivatives. With these log properties, we're not even talking about derivatives here. In fact, you learned these way before derivatives, a long time ago. So here, the third log property just says the power that's inside of the log gets multiplied to the front. Now you have to have the entire inside of the log raised to that power before you can multiply it in the front. But that's what the log property would say. So with those log properties in mind, they're actually going to be very helpful when we go to differentiate example 5. So in example 5, we've got y equals x squared plus 1, all in parentheses, and then times quantity x plus 3 to the half, and then all over x minus 1. Now if you had to just take the derivative of this, you'd start with a quotient rule, right? Because you have this fraction. Then inside the quotient rule, you're going to have a product rule. Inside the product rule, you're going to have a chain rule because you got this x plus 3 inside the 1/2 power function. It's going to be a big mess. So logarithmic differentiation is going to come to the rescue here. Now, what to do is inside of the name, logarithmic differentiation. First, we're going to apply the logarithm, and then, after using the log properties, we're going to differentiate. That's going to be the strategy here. Let's see how that looks. First, we're going to take the log of both sides of our equation. So we have ln, and we're just going to use ln for convenience. We have ln of y equals ln of x squared plus 1 in parentheses times x plus 3 to the half over x minus 1. So then for the next step, we're going to use those log properties that we just reviewed to break down the right-hand side, the log of these products and quotients and powers. We're going to break all that down into a bunch of littler logs, or smaller logs, using these log properties. Remember, the multiplication turns into addition, the division turns into subtraction, and the exponent turns into multiplication using these log properties. So by using all of them, we're going to have the log on the right side break down into log of x squared plus 1 plus 1/2 log of x plus 3, and then minus log of x minus 1. One thing I should mention is that when I write these L's, I'm writing them as script L's, just because then it's not confusing with like the number 1 or possibly an absolute value symbol. So I'm writing these as script L's. I know a lot of people get confused and think it's a capital I written in cursive, but it's not. It's a script L. So this is LN, not IN. It's LN, just to make that clear. So we used the log properties here to break down this log of a big function into the logs of smaller functions. And that's great because now we can take the derivative. We can differentiate both sides with respect to x, and it's going to be a much easier derivative process. So we'll take the derivative on the left side and on the right side. I'm going to write all the derivatives first, so I don't have to keep changing the color. So d dx of ln y equals d dx of ln x squared plus 1 plus d dx of 1/2 ln x plus 3 minus d dx of ln x minus 1. Now we're going to take those derivatives. Now the first derivative that we have to take is the derivative of ln y with respect to x. Here, y is implicitly a function of x. So this is a function inside of the natural log function. We're going to have to use the chain rule. So when we use the chain rule, we're going to take the derivative of the outer function, which is the log. Remember that the derivative of log of x is 1 over x. So here, since instead of an x we have a y, we're going to write 1 over y. But then we're going to write times the derivative of the inside, so the derivative of y with respect to x, because of the chain rule. This is a chain rule that's going on here, where y is the inner function. In fact, I'm going to highlight that again. This is a chain rule. Now on the right side, all of these derivatives with respect to x have functions of x inside of them. So these are just regular old derivatives. Now again, with the log of x squared plus 1, we're going to have another chain rule because we have the x squared plus 1 function inside of the log function. So there it's an explicit chain rule there. So we're going to have 1 over the inside times the derivative of the inside with respect to x, and that is 2x. This is another chain rule. In fact, all of these are going to be chain rules. I'll write it up. Chain rule, chain rule, chain rule, chain rule. So the derivative of 1/2 ln of x plus 3. I'm going to write the 1/2 there. We know that that's not going anywhere. That comes out of the derivative by the constant multiple rule. So those constant coefficients always just hang around after the derivative. So now we focus on the derivative of ln of x plus 3, which is going to be 1 over the inside times the derivative of the inside, which is 1. So 1 over x plus 3 times 1. Then we have minus 1 over the inside times the derivative of the inside. So we're always doing the 1 over the inside thing because the derivative of natural log of x is 1 over x. That's one of the basic derivatives to know. Okay. So far so good. Now all we have to do to find dy dx is solve for dy dx. We're going to multiply the y over to the right side, and then maybe simplify what we have on the right side. So here the 1 over x squared plus 1 times 2x turns into 2x over x squared plus 1. The next fraction we can write as 1 over 2 times x plus 3. All the bottom factors multiply together. We don't have to distribute it though. And then the last one is just 1 over x minus 1. And that is how you can write your answer. Now, here I've left the y as just y, but you could also replace it with the original function. So I'm just going to write a little note here that says this y right here is x squared plus 1 times x plus 3 to the half. It's the original function all over x minus 1. So we do have dy dx as just a function of x here if we replace the y. But on quiz or a test, if you want to just leave it as y, that's fine, because I know sometimes these functions are a lot to write, and so you don't want to be sitting there just spending all your time copying this function. All right, so that's logarithmic differentiation, one of my favorite techniques, because it kind of summarizes implicit differentiation, also talks about logarithms, and it's just kind of a nice little technique to know about. Thank you for watching, and see you next time.